Assalamu alaikum everyone. So Bismillah ar-Rahman ar-Rahim. So today we will discuss lecture number 3 of chapter 21, electric charge and electric field. And we will talk about the calculation of electric field due to continuous charge distribution. At first, let me define what means continuous charge distribution. So imagine a charge Q is made up of million of charges, million of electrons, for example. I can put all these electrons, that means the million of electrons at one point, and hence we will get point of charge. Or we can spread out these millions of electrons into larger space, and hence we have continuous charge distribution. So what means continuous charge distribution is the spread out of point of charge on the surface or on the volume on linear charge line. Okay, to evaluate the electric field of continuous charge distribution, we can do the following. Divide the charged object into small element of charge. It has a charge delta Q. We consider delta Q as a point of charge. For example, in this figure, you see that we have this shape, and we assume that this shape is charged. We will take a portion of this shape, and this portion of charge is called element charge delta Q, produces a delta E. Okay, then we will calculate the electric field due to one element of charge delta E. And then we will do the summation of all the vectors produced by delta Q. So in another word, you know that the electric field due to the element of charge delta Q at the point P is given by delta E equal delta Q over R squared multiplied by the unit vector R. The total electric field is the vector sum, of course. And then if we assume that delta Q tends to the zero, that means a very small element of charge. In this case, the electric field E produced by continuous charge distribution would be K integration of dq over R squared multiplied by the unit vector. So here what do we have? The electric field produced by a continuous charge distribution would be constant, Coulomb's constant, divided and multiplied by dq over R squared multiplied by the unit vector. Let's say this is the unit vector. And you know what means unit vector is a vector where it's equal to the vector divided by its magnitude. The magnitude of the unit vector, as you know, it's 1. dq is an element of charge. And R is the distance from dq to the point P where we want to calculate the electric field. Ke is Coulomb constant, which is equal 1 over 4 pi epsilon naught. And we assume that this constant is equal 9 times 10 power 9. And this is the electric field, as you know. So now we will try to calculate the integration of K dq over R squared multiplied by the unit vector. What did we have here? When performing such calculations, it's convenient to use the concept of charge density. What means charge density? We have 3 types of charge densities. Volume charge density, rho. Rho in this case is equal to Q, the total charge divided by the volume. So it's the charge per unit of volume. Its unit is Coulomb divided by meter cube. For an infinitesimal element of volume dV, the charge dq can be rho multiplied by dV. Let's talk about the surface charge distribution sigma. If the charge Q is uniformly distributed over a surface with an area A, the charge per unit of area sigma is given by sigma equal Q divided by A. For an infinitesimal element of area dA, the charge dq will be equal sigma multiplied by dA. The linear charge distribution lambda, if the charge Q is uniformly distributed over a line of a length L, the charge per unit of length lambda is given by Q divided by L. For an infinitesimal element of area dl, the charge dq will be lambda dl. You see here, based in our configuration, whatever its volume, surface, or linear, we have a different expression of dq. dq for the volume is rho dv, for the surface is sigma dA, for the line is lambda dl. Good. Unless we are done, now let's move to our examples. Example number 1, the electric field due to charged rod. The rod of length L has a positive charge. You see here that the charge is positive per unit of length L, and the total charge Q. Positive charge per unit of length is what? It's lambda. Yeah, it's lambda. Here we are talking about linear charge distribution. We're talking about rod. Calculate the electric field at the point P that is located along the long axis of the rod. That means our rod here in our case is along X. So that means the point is along X. And a distance A from one end, whatever it's on the right or the left rod. It's almost the same now when we take our point P is on the left side of the rod, and it's located at the origin of the XY coordinates. The distance from the point P to one end of the rod is called A. The length of the rod is called L. Now, what we're gonna do? We will take a portion of charge, an element charge dq. dq in this case is equal lambda dl. dq equal lambda dl. Our charge can vary along the x-axis, so dl will be equal dx, and dq in our case, this problem, it will be lambda dx. Why dl equal dx? Because the charge, the element charge dq varies along the x-axis on the rod. Okay. Now, what's the distance between dq and the point P? We call this distance x, and x can vary from A to L plus A. This position is called A plus L, and here it's A. So dq can vary from A to L plus A. Let's start the calculation of the electric field. Okay, what we're gonna do in our case? Let's start by the beginning. So we said that the electric field E equal K integration dq over R squared. As we said, we have to express this dq, then we have to express this R squared, and then we have to express this integration with the sides. At first, dq, in our case, we are talking about linear charge distribution. We said it's lambda dx. What about R squared? R squared, we said, it's the distance from the charge dq to the point P. In the figure here, the distance from dq to the point P, we said it's x, so it's x squared. What about the sides of the integration? The sides of the integration, we said our charge can vary from A to A plus L. So, and we can write our integration to be K integral of dq lambda dx divided by x squared from A to A plus L. And we are almost done. Lambda is constant, so we can write lambda, K lambda from A to A plus L, 1 over x squared multiplied by dx. The integration of 1 over x squared dx, it's known, so we can write that E equal K lambda multiplied by minus 1 over x, the primitive of 1 over x squared, from A to A plus L, and it would be K lambda factor of minus 1 over A plus L minus A. That's good. Minus 1 over minus 1 over A. Very good. So you see here that we have minus and minus, that we cancel each other, and then we will try to add these two quantities. We will multiply this by this and this by this. So what we're gonna get? So E, it's equal K lambda multiplied by minus A plus L divided by the product of the two denominators. So A plus L. So it will be, as you see here, we have minus A and A. They will cancel each other. So the result is as the following: K lambda L divided by A factor of L plus A. Now we are almost done. What do you think about this quantity? K lambda? K lambda, we said it's a Q, because Q is the charge density multiplied by the length of the rod. So we will get the electric field produced by our rod, in this case, equal KQ over A factor of L plus A. And we are done with the expression of the electric field produced by this configuration. Okay, let's discuss some special cases. We have a special case in this configuration if the point P is far from the rod. The point P is far from the rod. That means the distance A is big comparing to the length of the rod L. So let's come back to our equation. KQ over A factor L plus A. What we're going to do for this L, this L will be neglected. L is neglected. Okay, and our expression will be KQ over A squared. This expression of the electric field produced by the rod, positively charged rod, at a point P far from the rod is similar to the electric field produced by a point charge. Okay, so far from this rod, we can see the rod as a point charge. And we are done with this first example. This is the easiest case. Now we will discuss another case. A positive charge Q is distributed uniformly along the y-axis. So our charge now, our rod, is located along the y-axis, and the charge dq can vary along the y-axis. Between A and minus A, it's very easy. Find the electric field at a point on the x-axis at a distance x from the origin. Let me discuss, and as usual, I would like to draw the situation and discuss again the configuration. This is our y-axis, and this is our x-axis. Where is our rod? This is our rod. Yeah, the distance from the origin to the upper end of the rod is A, and minus A on the lower side of the, or lower end of the rod. We will take a portion of charge, an element charge that we call dq, and since the rod is positively charged, will produce an electric field. This electric field is outward and call it dE at the point P. You see that our vector has two components, one along x and one along y. Let's say this is dE y. Okay, imagine that we have another dE symmetric to the dQ symmetric to dQ1, dQ2 symmetric to dQ1. The same, there is an electric field produced by the second charge element. Let's say this is dE2, has two components, one along x and one along y. What do you think about the y component of the two vectors? Yes, good. They are equal in magnitude, opposite in direction, so they will cancel. At the end, we can say that the y component of the electric field produced by the rod, it will be 0 y due to the symmetry. Any point from the upper half of the rod produces an electric field. At the same time, there is another electric field produced by the lower half of the rod, where the two electric fields have two components. Both of them, they have component positive along x and along y, opposite in direction, and have the same magnitude. Their sum, of course, will be 0. So the electric field produced by our rod, it's only its x component, only the x component. And the x component of this vector is equal E multiplied, of course, by cosine theta. Where is our theta? Let's take this vector in red. And theta is also here. Let's now try to determine our distance x. The distance x is from the origin to the point P, and the distance r, it's from dq to the point P. And let me take this distance is called y from the origin to the point dq along the y-axis. So what will be this expression? This expression E of the rod in our case, we said it's E multiplied by cosine, and E equals K integration of dq over r squared multiplied by cosine theta. As usual, we will try to express dq, then r squared. Now we have another term, cosine, and then the integral. Let's start by the first term, dq. We said dq is equal lambda dl. Our charge q, dq, can vary along what? Along y-axis. So we will write lambda dy. Good. Lambda dy. And then our r squared, the distance from the charge to the point, it's called r. Let me take this triangle. It's right angle triangle. So we can apply the sine and the cosine. So our cosine is x over r. Before. R squared is x squared plus y squared. X squared plus y squared. What about the third term, cosine theta? Cosine theta is x over r. That means x over square root of x squared plus y squared. And khalas, we are done. We can take these three terms together to calculate the electric field produced by the rod. The electric field produced by the rod will be K integral lambda dy over x squared plus y squared multiplied by our cosine. The cosine is x over square root of x squared plus y squared. And we can get the following expression. Yeah. Good. So the electric field E produced by the rod will be K lambda x. What is our variable? The variable is y. So anything other than the y will be considered positive as a constant, sorry. Multiplied by the integral of what? Of dy divided by x squared plus y squared power 3 over 2. Very good. 3 over 2. Why 3 over 2? Because a multiplied by a power 1 over 2 will be equal a power 3 over 2. What means a power 1 over 2? A power 1 over 2, that means square root of a. So when you reach this step, you are almost done, because this integral is given. But before, our charge can vary from where to where? The charge can vary from minus a plus a. Okay? So this is our integral. This is, as I said, it's given. Yeah. it will be equal to 1 over a squared multiplied by x over square root of x squared plus a squared. So our expression will be k lambda x multiplied by 1 over x squared, 1 over x squared multiplied by y over square root of x squared plus y squared. From where to where? From minus a to this a. And like that, we got the electric field produced by the rod will be, cancel this x, k lambda over x multiplied by a over square root of x squared plus a squared minus a over square root of x squared plus minus a squared. This minus can be cancelled because we talk about something squared, power 2. This negative sign will go with this negative sign, and then we will get our equation k lambda x 2a over square root of x squared plus a power 2. Good. What do you think about this quantity? Lambda to a. Lambda to a, where lambda to a equal lambda multiplied by the length of the rod. And what about the charge density multiplied by the length? It's u. So our electric field produced by this rod on the point P along the x-axis will be kq over x factor of x squared plus a squared under the square root. And this is the expression of the electric field. Let me discuss some special cases. Let me discuss some special cases. First case, special case. P far from the rod. P far from the rod, that means the distance x is too much large compared to the length of the rod, A. So what means this? Let's come back to our equation. E equal to, kq over x multiplied by square root of x squared plus a squared. What we're going to cancel in this case? A is neglected. That means this expression becomes kq over x multiplied by square root of x squared. Square root of x squared, that means absolute value of x multiplied by x, that means x squared. So it would be kq over x squared. What do you think about this expression? This expression is similar to electric field E produced by a pointed charge. What we can say now? Now we can say if we are far from this rod, we can assume this rod to be like a pointed charge. Special case 2. Very long rod or wire. If we have a very long wire, in this case, what is the approximation? A is very big compared to the x. That means x over a is very small. That means x squared over a squared is very small compared to the a. It can be neglected. So let's start from our expression, kq over x factor of x squared plus a squared. This expression will be kq over x multiplied by square root of a squared factor of 1 plus x squared over a squared. Yes or no? Yes. So what we're gonna do for this expression, this will be cancelled and neglected compared to the 1. So the result will be as the following: kq over x multiplied by square root of a squared, that means multiplied by a. And what do you think about this q? How much we said q? Q we said lambda k lambda 2a. Now we can cancel this L from this expression, and we can get that the electric field produced by the rod will be 2 lambda k divided by x. You see that all the terms in this electric field are constant except this x. So when we are talking about very long wire, only the distance from this very long wire to the point P affect the electric field only. That's very nice. So this is when we are very long charger. Good, so we are done with the second example. Let me explain the third example. In the third example, we are talking about the electric field of uniform ring of charge. Here, we will talk about a ring. Before, we are talking about a rod or a wire, straight rod. Now we have a ring. A ring of a radius A carries uniformly distributed positive total charge Q. Calculate the electric field E due to the ring at a point P lying at the distance x from the center along the central axis perpendicular to the plane of the ring. Good. يلا. As usual, I would like to draw the figure again. This is the y-axis. This is our x-axis. What is our ring? This is our ring. Good. It's positively charged, positively charged. So the electric field produced is outward. Where is our point P? This is our point P. The distance from the origin to the point P is called x. When we take a portion of charge, an element charge, we will call this element dq. dq produces at the point P an electric field dE outward. This dE makes an angle theta with the x-axis. That means it has an x component and a y component. This is the x component, and this is our y component. This is our distance r from dq to the point P, and the distance from the origin to dq is called a, which is the radius of this ring. Now, let me discuss the y component. Imagine at the same time that we have another dq on this location on the opposite side. That means it's symmetric. dq. This dq2 produces an electric field also outward. This electric field dE2 has an x component with a positive direction and a y component. We can see here that we have an x component upward, a y component upward, and a y component downward. What happened to this y component and the total expression of the electric field will cancel each other. So we write E, the y component for the ring, equal 0. Why? Due to the symmetry of the problem. Due to the symmetry, the y component of the ring is 0. So only the x component of the ring we have in the final expression. So it's only the x component, which is E multiplied by cosine theta. Very good. What do you think about this expression of E? It's k integral dq over r squared multiplied by cosine theta. As we did in the example of the rod along the y-axis, we have to look for this dq for r squared, cosine, and then the integration with the signs. Let's start, in this case, let's start by r squared. R squared, as you see, we have right angle triangle, so that means equal x squared plus a power 2. What do you think about the cosine? Cosine theta equal adjacent divided by the hypotenuse. So x over r. So that means x over x squared plus a power 2 power 1 over 2. That means square root. Okay, now let's talk a little bit about dq. dq, if we change the location of dq from one to another location, if we take, for example, this dq here, we will get the same r and the same theta because we are talking about 3-dimension. If we take dq here, we will take the same r and we have the same angle. Okay, it's like this position, like this configuration. Yeah. At any point of the ring, we have the same r, same r, same r, same r, and we have the same theta also because we are talking about 3D. Okay, we have the same theta. So what we can say about this r squared and cosine theta are independent on dq location. So they will be considered as constant, and as a result, they will be out of the integral. So our vector E of the ring will be k multiplied, divided by x squared plus a squared multiplied by cosine theta. That means x over x squared plus a squared power 1 over 2 square root. That means the integral of dq. The integral of dq is what? What is the integral of dq? Is q. This quantity is only q. So E of the ring is equal kx over kxq over x squared plus a squared power 3 over 2. And this is the electric field produced by the ring at the point P lying on the x-axis. We have some special case. If P is far from the ring. If P is far from the ring, that means the distance x is very big, very large compared to the A. That means A is neglected. In this case, the electric field E produced by the ring is kxq divided by, we cancel this A squared, so that means x squared power 3 over 2. X squared power 3 over 2, that means x power 3. So kxq over x power 3. X power 3, and we have x in the denominator, that means kq over x squared. It's also similar to the point of charge. The same case, when we are far from this ring, we will see the ring as a point charge. The second special case at the center of this ring. Let's take paragraph 3. At the center. At the center, x equals 0. That means, that means E at the center equals 0. And we are done with this example. I think it's easy and it's also clear. Now, we will discuss the electric field produced by uniformly charged disk. We are talking about a disk now. Now we will move from linear charge distribution to the surface charge distribution. Okay? The example said a disk of a radius r has uniform charge density sigma. Don't forget that sigma is Q divided by the area. Calculate the electric field E due to the disk at a point P that lies along the central perpendicular axis at a distance x from the center of the disk. Okay. Bismillah. Okay, what do we have here? Let's try to draw the figure as we did before. This is our y-axis, and this is our x-axis, and this is our disk. Let's say the disk is here. On the surface of the disk, we have charge. It's different to the ring. When we take a portion of charge, for example, dq is here, okay? And when we take our point P is here. The distance from dq to the point P, dq produces an electric field at the point P. Of course, it's outward because sigma is positive. You see that we have an x component and a y component of the E. At the same time, if we take a symmetric element charge dq here on the other side, there is an electric field outward, dE. This dE has an x component along the positive x-axis and the y component. What do you think about these two y components? They will cancel each other because we have the same distance, same magnitude of the charge dq. So one upward, one downward will cancel each other. Good. Now, only the x component will be taken into consideration, equal 0. Why? Due to the symmetry of the problem. Only the x component will be calculated, is equal E multiplied by cosine theta. What is our theta? Let's say this is theta, and let's say this is our theta. When we take the distance, from the origin to the point P, x. When we take the distance from the origin to the point dq, we take it r. And what is the distance from the point of charge dq to the point P? To avoid any confusion between the r, we will take it as d. So our equation would be k integration of dq over d squared, now in our case, multiplied by cosine theta. Don't forget that this d squared is the distance from the point of charge dq, the element charge dq, to the point P. What we're going to do? Express the dq, d squared, cosine, sides, and integration. So it will be equal to, okay, at first we have dq, we are talking about surface charge distribution, so it will be sine sigma dA. dA, in our case, we are talking about disk. That means sigma multiplied 2 pi r dr. Second, d squared, in the right angle triangle, we have x squared plus small r squared. And cosine theta equal x over t, which is equal x over x squared plus r squared power 1 over 2. As we discussed before, let me see if d and cosine depends on the location. If we take another location here of dq, the distance r will change. The distance d will change and cosine will change. So d and cosine theta depend on dq location. So they cannot be considered as constant. Let's try to figure out our integration. Okay, so the electric field E produced by the disk will be equal K multiplied by integral sigma 2 pi r dr divided by x squared plus r squared multiplied by the cosine, which is equal x divided by x squared plus r squared power 1 over 2. Our variable is the r, so anything else than the r will be considered as constant. So we can write k sigma 2 pi x multiplied by r dr over x squared plus r squared power 3 over 2. Very good. This r can vary from where to where. It can vary from 0 to the radius of the disk, and we are This is our integral. This integral is given. It will be given. So it's minus 1 over square root of a squared plus x squared. So we can write k sigma 2 pi x multiplied by minus 1 over square root of x squared plus r squared from the 0 to the capital R. So it will be equal to sigma k sigma 2 pi x factor of minus 1 over square root of x squared plus capital R squared minus 1 over square root of x squared plus 0 squared. 0 squared, that means 0. Square root of x squared, that means absolute value of x. Now, if we try to develop this x, what we're going to get? We will get sigma k 2 pi factor of negative and negative, it will be positive. X over x, that means 1. Our x is positive, so absolute value of x will be x minus 1 over square root of x squared plus, sorry, here we have x, capital R squared, and we are done. This is our electric field produced by the disk at the point P along the x-axis. And we are done. Let me summarize here. E produced by the disk equal sigma k 2 pi factor of 1 minus x over square root of x squared plus capital R squared. Okay, and we are taking x as a positive. خلاص. If we discuss some cases, if P is very close to the disk surface. If P is very close to the disk surface, that means the radius R is very big compared to the X. That means X is neglected. Okay, in this case, P becomes sigma K 2 pi factor of 1 minus X over we neglect the x, that means x over r squared under the square root. This quantity, 1 over something very big, it's 0. So this quantity is 0. So our equation becomes sigma k 2 pi only. However, we know that k is equal 1 over 4 pi epsilon naught. Very good. What do you think about this 2 pi? And this will be cancelled. So it will be sigma over 2 epsilon naught only. Look at this expression. This is the electric field E produced by surface, a charged surface. Charged surface. Because when we are very close to the disk, we see the disk as a surface. Now we will take some cases. Let me talk about this first case. If we take two parallel plates, plus sigma and minus sigma. We take the minus sigma, negative sigma, upper plate, and the lower plate is plus sigma. The negative, let's say this is 1 and this is 2. Negative charge produces an inward electric field. So the electric field produced by 1 is inward, and here is also inward, which is constant. Okay, sigma 1 E1 in magnitude is equal sigma over epsilon naught. Okay, let's take in magnitude, which is sigma over epsilon naught. What about 2 now? The second plate produces an outward electric field. Why? Because it's positive. It's positive. and here it's positive sigma. The same E2 in magnitude is equal to E1 in magnitude over 2 epsilon naught. Sorry, I forgot 2 epsilon naught. 2 epsilon naught. So let's discuss on the upper above the upper plate, the electric field, one upward, one downward. They have the same magnitude, so the electric field is 0. The electric field in between is sigma over 2 epsilon naught plus sigma over 2 epsilon naught, which is equal to sigma over epsilon naught. And here also E is 0. So this is the expression of the electric field produced by two parallel plates with different sign in the charge. So out between E equals sigma over epsilon naught, out E equal 0. And we are done with this lecture. Alas, we are done with this lecture. Now let's move to some activities. A positive charge is uniformly distributed around the semicircle. The electric field that this charge produces at the center of the curvature P is in the x-axis, the negative x-axis, the y-axis, the negative y-axis, or none of the above. Okay, to discuss this situation, let's take two symmetric points. This is dq, and let's take another one, dq. Each of these dq, let's say this is dq1 and this is 2. Each one will produce an electric field outward because the charge is positive. This is dE1 and this is dE2. Let's discuss their x component. This x component, this x component. Both have y component downward. What is the total electric field? The total electric field has an x component equals 0 and the y component along what? The sum of these two vectors. So this is Ey along negative y-axis. So the correct answer is D. Let's discuss the second example. A circular ring uniformly charged with a positive charge Q is in the XY plane centered on the origin as shown. On the Z-axis, the electric field Ez equal E equal Ez multiplied by the unit vector K, which graph accurately presents the electric field Ez on the Z-axis. Imagine that our point is here, P. What did we say in the example of the ring? For the ring, when the point is on the x-axis, we said that the expression of the electric field is the following. No, this is for the disk. For the ring is this expression. Kxq over x squared plus a squared power 3 over 2. So kqx over x squared plus a squared power 3 over 2. Now, our point is along z. So instead of x, we will write only z. That's all. Okay, what do you think? What do you think if z is positive? The electric field, is it positive or negative? It's as a function of z over z power 3. It's positive. The electric field is E, z is positive. If z equals 0, it's as a function of z here. So it's 0. Along z is 0. What do you think if z is negative now? The electric field varies as a function of kqz. That means, and here we have z squared, so that means Ez is negative. Now, if z is positive infinity, it's as a function z over z power 3, so that means 1 over squared. E varies as a function of 1 over z squared, so which is 0. If z is negative infinity, the same, e turns to the 0. Okay, let's draw the variation of the electric field as a function of the z-axis. When z is 0, the electric field is 0. When z is positive infinity, the electric field is 0. When z is negative infinity, the electric field is 0. When z is positive, the electric field increases until a maximum value and then decreases to the 0. When z is negative, the electric field reaches its minimum and then decreases and then increases again to the 0. So this is our configuration. Let's discuss these cases. So the correct answer should be this. What's wrong in the first case? In the first case, when z is negative, we have electric field is positive, which is wrong. What's wrong with this? When z is positive, the electric field should be positive, but we have negative in the figure. And when z is negative, the electric field should be negative. We have a positive field in the figure, so it's wrong. What's wrong with this? We have 0 here. When z is 0, the electric field should be 0. And when the electric field is negative, when the z is negative, the electric field should be negative as well. And then this is wrong. And for us, we are done. Thank you so much, and see you in another recording.